I'm standing inside one of India's hidden jewels, the solid state physics laboratory in New Delhi. This laboratory has given India semiconductor devices in our latest satellite, the EOS-4. And you would be surprised to know, the first Indian satellite, Aryabhatta, also had semiconductors which came from this laboratory. The machines you see behind me are sophisticated instruments which are used by scientists here to give India some of the best semiconductors. These wafers are hard to get and these compound semiconductors are hard to make. If these were easy, then everybody would be making them. India deploys some of these semiconductors in its devices. It is the remarkable vision of the Defense Research and Development Organization that compound semiconductor research started in India decades ago, and India is a leading nation in this sector. I am at a facility that not only designs but also makes compound semiconductors, lab to fab, and that is the speciality of the solid state physics laboratory, part of the Defense Research and Development Organization. On this episode, it's all about understanding advanced semiconductors and to explain to us the complexities, and trust me, there are many complexities in this. We have somebody who understands end to end about semiconductors. We have with us Dr. Seema Vinayak. Namaskar, ma'am.
Namaskar.
Dr. Vinayak studied at the Punjab University in Chandigarh and also studied at the Indian Institute of Technology, Delhi. And one more claim to fame. She is just a handful of India's top-ranking scientists who are leading this interesting field of semiconductors. Thanks a lot for letting us in and showing us your facilities. Tell me a little bit about India's new semiconductor mission.
Okay, India's Semiconductor Mission, ISM, it's a very important first step to a long journey that I feel has to be paved with a very strong R&D backer, with a very good ecosystem balance, and also has to be shaped through very well carved out collaborations, because it is a mission that has the ultimate aim of indigenizing the commercial chips that form such an important part of our life today. Personally, if you ask me, I feel it is a long due step. It should have happened about years or decades ago.
A very general question to you. How difficult or easy is it to be leading a large team of creative scientists and yet be a lady director leading from the front? Is it challenging or is it easy?
I would say that being a lady does not hinder me in any way in leading or doing my role that I am doing. SSVL has a very good strength of ladies here. Almost 30% we have as lady scientists.
More power to you and more power to India's science being led by women. Let's go and take a look at some of the R&D facilities. Most of the semiconductors which we use, say, in mobile phones or televisions are silicon based. But the speciality of this laboratory is to work on compound semiconductors. What are compound semiconductors?
Okay. So silicon or germanium are elemental semiconductors because you have a single element in them. And I think germanium was the first semiconductor on which work had started way back in 50s. And then silicon came over. Germanium had its own reliability issues. Then silicon was taken over. And silicon, because of its abundance and because of the mature technology, takes this place of being everywhere. Compound semiconductors are semiconductors which have more than one element. And the biggest advantage is that you can actually tailor the properties of the compound semiconductors. It can have 2 elements, it can have 3 elements, it can also have 4 elements. You can add the elements and you can tailor the properties of the compound semiconductors or the advanced semiconductors that we say to meet the demands that are required, which may not be absolutely common or commercial, but which may be strategic in nature. These compound semiconductors, they emerge because of the specific requirements of defense or maybe space. And therefore, that technology is, even though the cost is more, that is not a consideration there. The consideration is the ultimate outcome. Performance. And silicon, when I said, as we worked for silicon solar cells, which you mentioned that Aryabhatta, we saw.
So the solar cells on Aryabhatta were
from SSPL.
Wow.
And I feel that one very important thing that our mentors had the vision of is that whenever you were doing a technology, do the material development also with it. So we were also doing silicon material development at that point in time, taking out silicon from silicon iron ores, but then it was not a economically viable solution.
Dr. Vinayak, what are the steps? You get an ingot from here, then you cut them. Explain that, and also about what are the other types of compound semiconductors.
So first is the growth of the ingot that you do in the reactors. You have different reactors for different materials. For example, here we have the ingot of silicon carbide that we have grown in this. The next step is to actually cut the wafers like this. So you slice the ingot into wafers, polish them, grind them, and we have something like this. This is a silicon carbide wafer. Other materials that we are working on is gallium nitride. This is a processed gallium nitride wafer.
I'm holding in my hand a gallium nitride chip. Very small, but within it, there are so many more components on it. Let's take a look how it looks like under a microscope. Wow, it looks very interesting, ma'am. Dr. Vinayak, this is the output from this microscope. What can we see here? And what would be the length of this?
Okay, so these are the different elements of a circuit which have been placed to get the desired output or the desired amplification from the circuit. So we have these high electron mobility transistors, we have the capacitors, we have inductors, and we have the transmission lines and the resistors. All of these have been put together to give us the...
What would be the average length compared to a human hair or something?
Okay, so one of these devices is just this much, would be 1 mm. But if you see, this is made up of a number of units. And if we look at one unit, I will just show you, then the gap between them is even fraction of a human hair, that less. And in that gap also, we have one more feature, which actually controls the performance of this.
And this is under an optical microscope, but we can also see how it looks like under an electron microscope.
Yes, we can do that.
Let's take a look at that. One of the things you mentioned where India lacked was a commercial fab, which is a fabrication facility, but you have a research and development fabrication facility here?
This is an R&D fabrication facility here, but the success of an R&D fab depends a lot on the availability of a production setup.
Let's go and take a look at your fabrication facility at the R&D.
Sure, sure.
We are now entering the semiconductor fabrication facility. So the gown done. Let's try go there. So we've entered what is considered the sanctum sanctorum for any semiconductor facility. This is the fab, the fabrication facility. Dr. Vinayak, what is a fab for a layperson and what are the processes which happen here?
Okay. So just now, when we were in the crystal growth area, we were talking about the ingots and the substrates that we were cutting. On top of that, we grow layers of the semiconductor, which are controlled at the atomic level. Once we have that, we have something like this, which is ready for processing. The devices, the circuits will be made on this. So now you can't see the atomic layers that have been grown, but that is what is responsible for the performance that we require. So this is the area where lithography is done. And lithography, let me tell you, is the heart of any fabrication of semiconductor. We have two optical lithography systems here. What we actually do is coat this material with photosensitive material that we call the photoresist, and then we have masks, different levels. So during one particular process, wafer comes here multiple number of times, depending upon how many layers we have to grow on them.
And what is our state compared to the world in the R&D facility?
Okay, so for gallium arsenide, I would say we passed on the technology to GATEC, and GATEC has been giving devices, MMICs. MMIC, I mean monolithic microwave integrated circuit. The complete circuit, I will just show you, is done on a very, very small chip. So gallium arsenide, we transfer to production. Gallium nitride, we are at par with what is available in a commercial foundry. So I think KU band, that is approximately up to 18 gigahertz. That is the kind of devices we are getting from the commercial foundries. That is what we are also working on.
So compared to the world, we are at par?
Yes, because this technology we started almost within a gap of 5 years of when it was started globally.
Dr. Seema, why do you need so much cleanliness in a fab and why so much water is used? Water and semiconductors and computer chips, they don't go together. Why do you use water?
If you see the huge circuits that we are making on these kind of wafers, a large number of them. So the dimensions that we are working at are very, very small, less than 1,000th part of a millimeter. So any particle which can fall on the wafer can actually kill the device, and just not a device, a number of devices. That is one reason. The other reason is that we want a lot of repeatability. So for repeatability, because we are moving so many wafers, they should face the same temperature and same relative humidity conditions in the fab to get the same performance. So that is why we need the cleanliness, why we need to maintain the environment. The other thing, as you said, why water? The wafer comes back to this level of lithography multiple times, and after each process the wafer needs to be cleaned, because what your device gives in the end as a performance is highly dependent upon its surface. So whatever,
that's why you need to clean it again and again.
Every time, multiple steps. So if it is, say, one lithography level, the multiple steps will involve using of water about, say, 3 to 4 times, because you'll clean it after developing, you'll clean it after etching, or you'll clean it after lift off. So a lot of water. And then when you go to a fabrication facility, which is a production facility, the number of cycles that the wafer sees of water washing is also standardized. That is also automated. So a lot of water. And the second part, why water? Because this condition that we have, as you see here, we have the temperature and relative humidity being monitored every time. You need a HVAC system, that is the heating, ventilation and air conditioning system. That system itself consumes a lot of water. The bigger the fab, the bigger is the amount of water required. That is that.
Now let's go and take a look at the other facilities in the fab. Let's go. Dr. Seema, all of this is your labor of love for years. Tell me what they are and what are they used for.
Okay, so what I want to show here is that you see this. This is not a semiconductor. This is a ferrite phase shifter. Ferrite is a piezoelectric material. I just have it to show what is the importance of what we are doing. So you see the size, and the size of this, many such components together will make one component that may be used, say, in a radar or for any transreceive module. But if you see these wafer, these pieces, these size of pieces hold some 7 components of this type on this piece. This is a semiconductor technology. And
so that size has been reduced to
not just
so much
size.
smaller.
Many components of this size have got reduced to this. So this is one complete power amplifier or maybe a complete transreceive module that we are
So
working
that is
on.
the magic of
That is-
semiconductors.
yes. And we have earlier worked on gallium arsenide technology, which is now totally in production at GETEC. This is what we have different circuits on a single 3-inch gallium arsenide wafer. And from such wafer, we remove such chips. You see a number of such chips. Yeah, and then these are packaged. You can see it here. They are kind of bonded using gold wires, and then they are used in the circuits. This is a processed GaN wafer that I've also already shared with you.
Lovely.
And this also has a number of circuits. And we can deliver up to 20 watts or 30 watts of power from a single circuit in this.
And from all of this,
Yeah.
then next stage is
Yeah.
full-fledged devices.
Yes, yes. These are our packaged devices, delivering more than 100 watt.
Having seen the clean room and the small semiconductors, let us now go and take a look at sensors and how the stuff is actually being used by India's armed forces. Let's go. Why do you need so many equipment, Dr. Vinayak, and what are these?
These are equipments that we call are the characterization tools. And whether it is material or whether it is the device or the circuits, we need to characterize them at different stages. And all the tools around you are actually the characterization tools.
And from here, let's take a look at your sensors and the actual stuff which is going out to the public. Let's take a look. What is this, ma'am?
This is a silicon MEMS G switch. So silicon has its own electronic properties, but it also has a lot of mechanical properties, because of which you can make small mechanical, electromechanical systems from micro electromechanical systems with this. So here we call, this is a G switch which actually protects the accidental detonation of any ammunition. And this has been designed here, and we have fabricated at our Bangalore setup called Star.
So this is essentially to protect India's ammunition not to get detonated before we want it to.
Right, right.
What is this e-Nasika, ma'am, and what does it do?
So this is a sensor. This actually can detect very small concentrations of chemical warfare agents in the air. And it will give an alarm and also give a signal on the screen. I can show you. You see that it has shown that I have shown it, this blood, the choking agent and the
Blister agent. So this is very useful in a situation of war. Handheld can be carried by our soldiers in the field.
Yes, yes.
And developed it.
SSPL completely, and it has been tested at DRD. Well,
Very nice. Thank you. And what is this, ma'am? What is N-Nasica?
Okay, that we call as E-Nasica, this we call N-Nose or N-Nasica. Basically what we have here is another sensor which is based on carbon nanotubes, and this has been designed for the testing of explosives. Basically most of the explosives, they break up into nitrous oxide or ammonia. So this has been designed to check nitrous oxide and ammonia. But we can also train this system to give us any alarm due to sewage gases or due to any other chemicals.
Air pollution? Because that can also be, because that's also there is.
So that is a kind of a spin-off use of this, civilian use of this.
The solid state physics laboratory not just works on gases and explosive detection, but also on issues of Himalayan proportions. Can you tell me what this is, Dr. Vinayak?
These are acoustic emission sensors, and we place them here. This whole thing called the arrestor goes into the snow. And
So this is for avalanche detection.
yes, and we have the data acquisition here, and it can detect the conditions that may cause an avalanche. in a
So
given-
early detection of avalanches using technology developed by your laboratory?
Yes.
And is it being used anywhere?
Yes, we've deployed these systems in Manali. We've deployed them even in J&K. And this last year, there, 4 of them have been deployed.
This DRDO facility also works on lasers and lasers to protect India. What can we see here, ma'am?
We have these laser diodes, semiconductor laser diodes, based on gallium arsenide, the compound semiconductor that we were talking about. This technology has been developed at SSPL, and you see the laser diodes packed in different packages. These are C mount and F mount, and if you see a small strip here, that is the laser diode.
And this is deployed for fencing
For
around
fencing.
cantonments?
So this is, yes. So this is a fencing module. On one side we have
So
the
you'll
laser.
put a laser from here, and on the other side you'll have something, and if something cuts through it, then it would give a signal. So something like this to protect our cantonments which have large areas.
That is one
And what
application.
is this?
This is, you get the laser output through a fiber here. There's a
Yeah,
thin
yeah, yeah,
fiber
there's a
you're
thin
seeing.
fiber.
You can use these to detonate explosives.
Let's take a look at other aspects of laser being researched at this very fine facility. Dr. Seema, what do we see in these glass tubes with water and some kind of a light passing through it, a green colored light?
Yeah. So just now I talked about SSPL being involved in gallium arsenide laser diode fabrication. Our next activity is to do gallium nitride laser diodes, and those are used for underwater communication. So here we are just trying to show, this is just that you can actually communicate data. This is to show data, and you can communicate sound.
So here, a laser light is being generated here,
Yes, and it is getting detected.
and it is passing through this tube of water and detected on the other
Yes,
side.
the ultimate use of this is in the underwater undersea communication. You can have the deep autonomous vehicles, communication between submarines. That is the purpose for which we are doing it. I invite you to speak something and see how it happens.
So essentially, when I say something and it's being transmitted through this box into this light as a laser, so if I say something and the laser is passing through, the sound will be heard. I'm going to say, watch Life and Science with Pallav Bagla. You can hear the sound. Now I'm going to cut the laser and still speak. Watch Life and Science with Pallav Bagla. So futuristic communication using lasers. Now let's talk about how semiconductors are likely to play a big role in this century. Dr. Seema, we've seen your compound semiconductors. We learned a bit about silicon semiconductors, lasers, communication, devices, satellites. Will, and sensors, will semiconductors play a big role in 5G, electric mobility, and in solar cells?
Yes, there's no doubt about that. We all know how important place semiconductors have in our life today. And 5G is the future of mobile communication. And that is one place where we see that gallium nitride can play a big role. So one can say that, yes, that could be a commercial use, civilian use of gallium nitride.
And what about electric vehicles and
Electric
mobility?
vehicle, yes, electric vehicles, silicon carbide, gallium nitride, they have a big role to play there. So that is a different technology for electric vehicles. You would need power conversion. So that technology for civilian use has to be developed and then taken to industry.
And so, bright future for people who are pursuing semiconductor research and are looking for jobs in the semiconductor area.
No doubt, yes.
Thanks a lot for speaking to us, Dr. Seema.
Thank you. Thank you for giving me this opportunity to speak to you.
What a pleasure seeing such an important laboratory quietly working in the heart of New Delhi and protecting India in so many different ways. Thanks a lot for speaking to us, ma'am.
Thank you. Thank you so much.
From sand to silicon to gallium arsenide to gallium nitride and to wafers and chips. The journey of semiconductors is complex. There's physics, there's chemistry, there's material science, and all of them have to marry together. And the solid state physics laboratory, which I call the hidden jewel of India, has done that remarkably over these years. One of the only facilities in India which truly has a lab to a fab. India is investing heavily in its semiconductor mission. The semiconductor mission is powered using silicon. But advanced semiconductors are going to come from facilities like this one. The future is here and now. Keep watching India Science.